So first of all, his name is David. His surname is Pilarski. And yeah, that's definitely him. And he's going to ask a very important question. So what's next? But before that, let me say that he has finished automation and robotic studies. But from the very beginning, as he says, he was passionate about C++ language, which probably means that this will be the topic today. So currently, David, he is a senior software developer in TomTom. In his free time, he's blogging about the C++ and gives talks on local meetups. He said that he's renovating his house, he's actually building his house, so he's already tired. I hope he'll have enough of energy for today to present the topic. And the topic is once again C++ 20 coroutines for the very last time, but now we're looking into the future. So what's next? That is the question. David, this is time for you. Thank you very much.
Okay, thanks. So let's then get started. So I'm David. The topic is C++ 20 coroutines. What's next? And actually, you cannot yet see the presentation. Yeah, there it is. Actually, it's more like C++ 23 coroutines, but I wanted to keep the title consistent with the previous one. Also, some time ago, I joined the standardization committee, and I thought that it would be good to start sharing the knowledge. So I thought CodeDive is a good place to share the knowledge. So I thought, like, what can I share with you today? And on the last CodeDive and any other CodeDives, there were no coroutines topics at all. So I thought, yeah, that's the topic I want to have. It will be a unique one. So guess what? This is how I became fourth presenter today that presents something about the coroutines. OK. So yeah, I'm David. I'm working for the TomTom. I'm the member of the standardization committee, and I'm writing a blog about the C++. I'm not posting very regularly, but if you are interested, you can have a look. You will find also coroutines materials there. And that's our agenda. So we will have a quick refresh about the coroutines. So that's going to be the part that you probably heard about on the previous speeches, but still we need to go through that for those of you who didn't attend any previous coroutines talk. And then we are going to go through the three topics that are issues in the current coroutines, so the coroutines as we know of C++ 20. So this is asynchronous RAII. We all know RAII, but in the space of the asynchronous operations, there's no such idiom. Then we will have a look at the RVO for the co-await expressions and non-tail call optimization. We will have a look at what it means, what it is. And if any of this issue you will find particularly interesting, then these strange numbers are the numbers of the proposals that fix the issues. So you can track it down on Google later on. If it's about the questions, hold your questions till the end, because then you will get the microphone, so you will be heard. And if you really want to ask something immediately, you will need to be very loud so that I can hear you. OK, so let's start. What's the coroutine? So the coroutine is a generalization of the function. So we need to know what the function is, and function is a subroutine. And we need to know what the subroutine is. So basically, when you have a subroutine, you have got some expressions, some statements that are packaged into some units. In case of the function, it's just, it's a block of the code that has its name, has got its arguments, and this function will produce us some result. Now, coroutine is a generalization of that, and we can perceive that as if we are extending the API of the function. So API of a function is that we can call a function, caller can call a function, and function can eventually decide to return. Coroutine, the same. We can call the coroutine, we can return from coroutine, but we can more. The most important is that we can suspend and resume it, but also create and destroy it. And the reason why we can create and destroy it is that when we suspend and resume the coroutine, there's going to be some allocated state for the coroutine, and creation and destruction of the state we will call creation and destruction of the coroutine. So those are the flowcharts, how it behaves. Caller calls the function, function eventually returns, unless it's not no return function. Call the coroutine. Coroutine can eventually return. After you return from the coroutine, you cannot resume it. But also you can suspend the coroutine from within the coroutine, and eventually you can resume it later on or kill it. And if you want to create your own coroutine types, it's not going to be easy for you, because C++ provides keywords only, and it's the developer that needs to implement what the keywords actually do. And this means that you need to implement your promise type, so you need to implement at least 6 functions there. The co-await keyword, you need to implement at least 3 functions, which gives you, like, at minimum 9 functions to implement. So you need to know 9 functions to be able to implement the coroutine, to know how those functions interact with each other, and so on. Looking at the coroutine is the same like looking at the function. So there's no difference from the declaration point of view between the coroutine and function. So whether or not the function is a coroutine depends on its definition. So it's an implementation detail. Now, how the compiler knows that the function is a coroutine? It has a look into its body. If it finds any of the keywords, co-await, co-return, co-yield, it says, oh, so you are a coroutine, actually. And then if compiler decides that this function is a coroutine, then it checks if the return type has a special implementation for the coroutines. So for the return type to have a support for the coroutines means that it needs to have a promise type. And this promise type can be a member of this return type or the member of the specialization of the coroutine traits of the return type. So a compiler will be looking for the promise type in the return type : promise type, or stored coroutine traits return type : promise type. Now, the promise type is something that controls how your coroutine behaves. So you have got things like initial suspend function that returns an awaitable. Awaitable, we'll talk about this later. Basically, you can say whether or not we should suspend our coroutine at the beginning. Same about the end of our coroutine. We have got the getReturn object, which knows how to create the returned object. Unhanded exception: if any exception falls out of your coroutine and you don't catch it inside the coroutine, then unhanded exception is going to be executed, so you can decide what to do next with it. Then you implement your keywords. Co-return with non-void expression gets translated to the return value with some argument. Empty co-return is going to be translated to the return void. Co-yield on some non-void expression is going to be translated into the co-await. Yield value, and the result of this yield value goes as argument of the co-await expression. So now what the co-await is, it's more complicated than the previous keywords. So the algorithm that compiler does when it meets the co-await is like following. First, it will be looking for await transform function in the promise object. If it exists, it will be invoked. If not, then not. And what it produces needs to meet the following properties that we'll list in a second. And if it's not, then argument of the co-await expression needs to fill these properties. So it needs to have operator co-await inside it as a member, or it needs to have operator co-await there needs to be a global operator co-await that takes this as the argument, or it needs to be an awaiter itself. And being an awaiter means that it needs to have 3 functions implemented. Await ready, that returns true. So, maybe awaiter is a guy that knows how to wait on things that we are waiting on. So await ready is a function that will tell the compiler, the program that we write, that what we are waiting for is actually ready. There's no reason to wait for that. Then if it's not ready, then the suspension happens, and we need to implement await suspend function, and it can return void, in which case our coroutine always suspends, boolean, in which case our coroutine conditionally suspends, or another coroutine handle, which means that our coroutine gets suspended and another one gets executed. And the coroutine handle is a handle to the coroutine, like the name suggests. There's also an await resume function. The result of the await resume function is the result of the whole co-await expression. So once what we are waiting for is finished and it produces us some value, we can get this value with the help of the await resume function. Now, what's the coroutine handle? Coroutine handle, as I've mentioned, it's a, like, you can imagine that it's a pointer to the coroutine dynamically allocated state, but it's actually a wrapper for the pointer. It can be empty, so it's default constructible, and it's constructible from the null pointer. You can assign null pointer to it. You can take address of the dynamically allocated state, but also you can create coroutine handle from this address. There's a Boolean cast operator, which returns true if the coroutine handle is not empty, and false otherwise. Done function. Done is true when we are suspending on our final suspend. And of course, we need to be able to resume our coroutine handle, and we'll use function call operator or resume function for that. Finally, we can destroy our coroutine. And the thing to remember is that we need to call this function like manually, because coroutine handle is not an RAII object, and it's not going to invoke it itself in its destructor. Then we have got specialization for the promise types. And the reason we need it is that we will very often have a need to get to the promise object from the coroutine handle and be able to create coroutine handle from the promise. So we have got a from promise static function that returns a coroutine handle given the promise object, and we have got promise function that returns us the promise object. Why do we need those coroutines at all? So first, you can hide asynchronous code. So the previous talk was very nice about how you can hide things under the co-await. You can hide state management. So basically, if you write your code right now, you need to have some state that's going to be shared across different like function calls, for example. Then you are going to manually determine what the state is going to be. And you are going to have some kind of a shared pointer to that. With the coroutines, what's the part of the state is determined by the compiler. So in the coroutine, we can have multiple suspension points. If lifetime of the variable crosses those suspension points, then it's a candidate to be a part of the state of the coroutine. So that's it about the refresh. So now we can go to the proposals. First, asynchronous RAI. RAII, resource acquisition, is initialization. I'm not sure how it is in your case, but if I didn't know the C++ and I would read the resource acquisition is initialization, that wouldn't tell me much. But fortunately, we are from the C++, we know what it means. So when we initialize the object with some resource, then this object should release this resource when it's destroyed. That's quite a common thing. We have got examples like smart pointers, like streams that automatically close the file when they are destroyed, and stuff like that. So what's different about the coroutines? So let's have a look at the example. So we have got a read file. This is a coroutine because it uses co-await in its body. It's going to return a task, so this coroutine is a task. And it's not that kind of task that you could be looking at on the previous talks. It's the task that is going to be standardized, most probably as a part of C++23. So the only operation that you can do on the task is the co-await on that. There's no like resume function and things like that. It's a task as if it was from the CPP Coro library. We are going to return a content of the file from this coroutine. File is given by its path as the argument. So first what we do, we asynchronously open the file, we asynchronously read the content of this file, we asynchronously close this file, and we co-return the content. So here we have got no mean to automatically, asynchronously close the file. There's like no mechanism in C++ that we could do that manually, right? So in case of async read throws, for some reason, you are going to have a resource leak. Because of that we do not have this RAII, we are going to have lots of issues, especially when your function gets big. You will want to do like early returns from the coroutine, throwing an exceptions and things like that. Every time you will need to remember to manually free your resources. Yeah. But in case of the coroutines, it's even worse than what we have seen on the previous slide. So this slide is, those are all those issues that you would have in C++ if you didn't have an RAII in the synchronous world. But there is even, the situation is even worse when it comes to asynchronous operations, and we'll have an example of that. So we have got a following scenario. We have got a lines coroutine, and it's going to be a generator. We are going to return line by line from the file that we are giving as the argument. So we have got input file stream. It creates a stream. It opens the file. And you are creating the line object. That line object will be holding our line that we read from the file. And as long as there is some line to be read from the file, we are going to return this line to our caller. And eventually, when we finish our coroutine, the stream closes the file. So that's good. But this is a generator. It's lazy. So one of possible usages of that is that we iterate over this generator, but we do not consume all the lines that are in the file, right? So we can say that if we found our line that we are looking for, we can exit this for loop, because there's no point in reading whole the file if you are not interested in its content. And we hit the break. We hit the break, we exit the for loop, and we are destroying the coroutine. At this point that we are destroying the coroutine, not all lines from the file might be yet consumed. So when the generator type is destroyed, in its destructor, it calls coroutine handle destroy. So coming back to our coroutine implementation, this is the destructor of the input file stream. This is what happens when loop is finished, so we consumed all the lines from the file. And on destroy, fortunately, this destructor also is going to be called, right? Now, exactly the same scenario, but this time our generator is asynchronous, and we are going to do everything asynchronously in this coroutine. So we asynchronously open the file, asynchronously read line from this file. We yield the line that we read, and at some point we are asynchronously closing the file. So the same. This is our cleanup. Then when you consume all the lines, that's fine. Then we hit the async close. So resource is freed. But now if you do early destroy, there will be no cleanup, because closing a file is not part of any destructor, so it's not going to be called by any means. So how can we currently, as of C++20, deal with this issue? So now async generator needs to implement destroying the coroutine differently than other types, other coroutine types. So before it destroys the coroutine, it needs to resume it one more time to give it a chance to do the cleanup. Also, the async generator type needs to have a little bit different implementation of the coyield keyword so that it returns the cancellation token. So the async generator type, before destroying the coroutine, resumes the coroutine, passes the cancellation token. So inside the body, we can check this cancellation token and react as needed. Right? So if you cancel our coroutine, we can check it, we hit the brake, and we then do the cleanup. So what's the proposed solution for this issue? We'll have something like a destructor, but asynchronous one, and it will be called tilde operator co-await. And it's going to produce us a awaiter. Then the co-await keyword will create a scope. At the end of the scope, the result of this operator co-await is going to be co-awaited. And now instead of destroy, you will invoke the function setDone that will automatically resume the function for you. That's how this coroutine can look like after adoption of the proposal. And the reason I'm saying it might look like this is that it's not yet clean how the syntax is going to be here. So this is a case where we have the co-await keyword being moved at the very beginning of the line. So the scope it produces is the same as the scope of the variable opened file. So at the same scope, when this scope of the open file finishes, then we will do asynchronous close of the file. So now this is going to happen as a part of cleanup. It doesn't matter if the cleanup will be will happen because of some thrown exception or something else. It will always be executed just like right now destructors are executed. So currently it's difficult to implement asynchronous generators, and it's not only difficult for the library implementers, but it's also difficult for like regular people who will be using those types. And if you're in the C++ and like every time we write something, we usually want to do some RAII. Then if you introduce a feature that doesn't have an RAII, it seems like some issue. But with the adoption of the proposal, the above is going to be solved. Another possible syntax for the solution would be to create something like co-using, and then you will create your scope explicitly by creating the parentheses. Okay. Now, RVO for the co-await expressions. So RVO stands for return value optimization. So basically, it means that we can save some time by avoiding some unnecessary copy and moves. So the way it works is like here. We have got some function foo. It returns us a vector of 5 integers. Now we are going to invoke the foo, and we are going to assign the result to the variable named underscore. And since C++17, we are sure that this kind of RVO will always happen. So we are sure that there's no copy and no move construction in here. How it happens? So our regular function foo, that normally returns a vector and has its body, will be a little bit transformed by like the end product of the compiler. So in the end, we'll end up with some function foo that takes a pointer. This pointer will point to the place where result is going to be stored. And inside the body, we are just doing in place new. This is how we avoid the unnecessary copy and unnecessary move. Now, why think like this is not possible with the Cortines? Whenever we say we have got an expression like co-await whatever, in this particular case it's co-await task, it's going to be transformed into this strange creature on the right. So first we are going to produce a waiter, and this transform function is hold this algorithm that compiler has. So first it's going to check for the await transform, then going to check for the co-await operators, and so on. Finally, when it manages to produce the awaiter object, it will produce it will invoke those three functions. This await ready to check whether or not what you are waiting for is ready. Await suspend if it's not ready, because await suspend is something that is going to, in case of task, execute the task. And await resume to get the value that's produced by the task. Now, the place that we produce a value is the await suspend function. So at this point, we are suspending our coroutine and start the coroutine of the task that we are waiting for, right? Eventually, this task is going to go to its end. It will do co-return something that will produce us a value. But the thing is that it's not going to immediately return this, because it does not know where to return this. So it needs to preserve this value in the promise object until the await resume, right? So the issue is that we produce value in one place and return this value in another place. Just if you had a class with function produce value, which will do all the calculations, but it will not return the value it produced, but it will have another function called get me the result that will return the value. So it needs to store this result in it. So how can we resolve the issue? So the issue was that we get this value from different place. So if our await suspend would be able to, would know where the result is going to be stored, the await resume would not be needed anymore. So await suspend now will know where the result is going to be stored, and is going to create it. But then we cannot just remove the await resume, because in case our await ready returns is not ready, and the other way, if what we are waiting for is ready and there's no reason to enter the await suspend, we will never produce the value, right? So we would have a variable with some name equals co-await some expression, and in case what we are waiting for is ready, we would never produce the value. So we need to remove the await ready as well. So now we are left with await suspend itself. Await suspend also needs to handle the case when what we are waiting for is ready. But there's like another issue in that. If we remove this if statement, then we will unconditionally always suspend the coroutine and always resume one, right? So those things in those brackets now are unconditionally executed. Here, they were conditionally executed. And in some cases, it will be some kind of... So being able to avoid those suspensions and resumptions simply saved us some time. So we have got possibility to enable the RVO, but it has got its cost in the other place. Also, the coroutine handle now needs to know about where the result is going to be stored. Plus, it needs to know how to create this result. So there's the setValue function that will create the result where it's going to be stored. SetValue from, where we can do like in-place construction. We are just passing the constructor arguments. And if we fail to create the result, we are going to call the set exception. And the reason that we need to have those three functions is that previously we could manually check that in the await resume. Now we have got no await resume, so compiler needs to generate some code for us. So compiler will generate the code that checks whether we produced a value or exception. If it was an exception, that it will rethrow it after we exit the await suspend. So this is how our promise type might look like after this adoption of this proposal. We have got a return value. It accepts anything that we can construct the result from, and we are just calling the set value on our coroutine handle, and that's it. Second overload of the return value is we take arguments that our produced value would need to be created, and then we invoke the set value from function with those arguments in place. The original proposal also proposes something that it will split the coroutine handle. It will split the coroutine handle into the suspension point and continuation, but just for simplification, we can say that it's just the coroutine handle that knows where the result is going to be created. And the funny thing is that right now, co-await, whenever we are saying co-await anything, the compiler knew what is going to be created because there was the await resume function. So the result of the co-await expression was the result of the await resume function. Now there is no await resume, so compiler does not know what's going to be created. So the proposal proposes to add member await result type to the awaiter so that compiler can know that. So inside the awaiter, we can say using await result type equals integer, so that compiler knows that we are going to return integer from the co-await expression. So we have got a very simplified awaiter concept. There were three functions. We have got one. We have got RVO optimization, so it's a benefit. So there's no variable created, temporary variable created. But also because we had to preserve this temporary variable in the promise, and the promise is part of the dynamically allocated state of the coroutine, also we end up with smaller allocations for the coroutines. The issue is that when we remove await ready, we always suspend the coroutine even if it's not needed. And this RVO that normally in the regular functions happens automatically, now, well, it's not maybe that big issue, but we need to manually implement this RVO. And the last one, non-tail call optimization. Right now, it's not possible to have a promise type that has return value of t and return void at the same time. And you would say, yeah, that's normal. You either return value or return nothing. So why would you even need that for? So the thing is that with regular functions, we are used to thinking from the function, we either return void, in which case we can do only empty returns, or we return value, in which case we cannot do empty return. We need to return something. But if it's about the coroutines, then it's not a return, it's co-return, and it has got a different semantics. And you might actually want to have both of them implemented. So, why I would like to have it? I have got coroutine foo that is the task of integer, co-returns 42. And another coroutine start that is of task void. Inside the start coroutine, I'm calling the foo coroutine, and I'm printing the result. At the end of the start, I have got implicit co-return. So this one is going to be translated to the return value call. This one is going to be translated to the return void. So, how we would like to implement it? We would like to have one promise type that has both return void and return value, but they are constrained so that one is not available when other one is. But that's not the way it works. So compiler takes a promise type, and it only checks for the names that are in those promise types. It sees the name return void. It sees the name return value. It won't even check the constraints and say, no, you can't do that. So the way we need to implement it, we need to have specialization of the full promise type like that. So we have like general implementation of the promise type and specialization for the void. But this was like minor issue. The second issue is like more important. So if we could have both return value and return void at the same time, we could always do something like non-tail call optimization. So what's that? I've got a coroutine bar and coroutine foo. They are of the same types. First one returns 42, and second one returns what another one returns. But I can implement task of integer in such a way that I can omit the co-await at the co-return. So here's the difference. The left example is a tail call. The right example is no tail call. So what's the difference in their behavior? So for the regular tail call way, so this left one is going to behave like that. We have got a coroutine foo. It co-awaits on coroutine bar, which can co-await something else and something else. Eventually, those coroutines run to its end. They are going to co-return, and they will destroy the frames that are not needed. So the longer the chain call, the more coroutine frames we need to have allocated, and we can destroy the coroutine frame only after the coroutine was co-returned. Now, in the other case, we can be a bit smarter. So the coroutine foo creates coroutine bar, then it deletes itself and resumes the coroutine bar. Bar creates bar 2, deletes itself, resumes bar 2. Bar 2 creates foo 2, this deletes itself and resumes foo 2. And foo 2, when co-returning, will return to the caller of the foo. Now, no matter how long this chain is, at most 2 frames will be allocated. And you can implement it right now, but only for those coroutines that do not allow to do co-return void. So, for this example, it's not going to be possible. We have got a coroutine display text that does empty co-return, so it wants to do return void. And we have got another coroutine display file where we asynchronously read the file, and then we co-return the like nothing. We don't return nothing. But this is going to be translated to the return value function, because there is an argument to the co-return. So it's not empty co-return, it's co-return with something, so it's going to be translated to return value. So when we try to implement it, we have got return void, we have got return value, and they both cannot appear in the same scope. So after accepting this change, we'll be able to simplify a little bit implementations of the promise types and make it possible to always do non-tail coroutines calls like for every types of coroutines. And that's it. Thank you for the attention. And special thank you goes to the Gornishanov and Louis Baker for creating C++ coroutines. And if you are interested in some further reading, you can read Louis Baker's asymmetric transfer blog. You can read C++ draft. You can read also my blog, where I also describe how coroutines works. You can see the coroutines proposals. And if you do not like reading and prefer watching, you can see some video of the James McNally's Introduction to the C++ Coroutines, any video of the Gornishanov, or to be also Coroutines, what can't they do? So it's a questions time.
Or you can ask a question to Dawid right now, so this is the best moment to do that. But before we do it, let's do it as we always do. Let's give a warm applause. Thank you, Dawid. Folks, any questions from you? I can see one person moving downwards, so I'll just head north. There we go. Hi, what's your name?
Hi. So you showed a bunch of proposals that changes the way we implement coroutine types and promise types, etc. And how this proposal goes through the backward compatibility. So if I implement batch of coroutine types right now, how would it impact me if this particular proposals landed?
Okay. So we had 3 proposals. So this one is backwards compatible, right? You couldn't have return value and void at the same time. Now you can. That's okay. Then we had an RVO and RAII. So either we can have backward incompatibility, or we can support both approaches, like the old one and the new one. So yeah, like you can have it backward compatible by like having multiple choices. Either you go with one await suspend function and you provide only one, or you provide all of 3, and then the code that's generated by the compiler is different.
It answers your question, right, Martin? Okay, thank you very much. I can see one more colleague coming here. Hello, what's your name?
Hi, Jan.
Jan, again.
Okay. So hi. So the problem with the RIE was that I guess we cannot, the destructor cannot be a coroutine.
Yes.
And do you know why? Like if we imagine that destructor could be a coroutine, it could, for example, dispatch the async close and then just destroy itself. Like the tail call optimization did something similar, right? Like it called some coroutine and then it destroyed itself. Why would it be possible with the destructor and have the same RIE as we are used to?
Okay, so right now you cannot return like anything from the coroutine. So, and to be able to co-await on the coroutine, you will need to return awaiter. And it's not the same thing to do co-await on the result of the function. It's not the same to do co-await on the result of the function than doing this co-await inside this function that we are calling. Those do different things. So if we would allow for the structures to return the value and return the awaiters, and we would do co-await on that, then there's a question: what with like containers? What's going to happen with the containers, where at the end you are going to delete all the objects, right? Does this kind of answer your question?
It wasn't like destructors not returning anything. It was more like in a destructor I would call
co-await.
Yeah, I would. Would I have to really call co-await? Like I would just call async close, which is a coroutine which closes a file. I don't know. It's just an idea, but I was interested. Like, why cannot destructor call a coroutine?
Sure, I get it. So here we've got some example of the coroutine. Bar is a coroutine, but you can co-await on the result of the bar, and you can call bar itself, but it will not execute any of the statement inside. It will just return you the task object. Right?
Oh, right, yeah.
So just calling this inside the coroutine is of.
Yeah. So we would have to call co-await to run the async close, and which gives us the problem that we have a waiter object inside the destructor and it gets destroyed. Okay, thanks.
I'm happy to see that you have the clarity because I totally do not understand what you're talking about, but thanks a lot for that. Okay. Any other questions, guys? All right, so what's your name? Zbyszek.
Yes. So I also would like to ask about the structures. And I have one concern because what if this line reader is, for instance, we are reading from the socket, and after getting what we expect, we don't get nothing else. I mean, the socket is still open, but we don't get any input. Will it hang? I mean, this async read line.
Okay.
So we get, for instance, we get the what the line we expect. So then we wait.
Okay. So, what if you read from, for example, do I understand your question correctly? So, if I would read, for example, from the terminal, then what happens when I do this async read line, and I still didn't press enter on this in the console, right?
No. You read one command, and the command is exit.
One more time.
So that you read one line, and the line is exit command. So the caller of the coroutine is exiting. How he can stop this? Close the file descriptor or socket.
Yeah. So this is the place where I'm closing, right? So right now, when we don't have an option to like, when you destroy the coroutine, right now, just call the destroy, you are going to have a resource leak. Now, with the adoption of the proposal, when you call now no longer destroy but set done, the co-await on async close is going to behave the same as if it was the destructor. So it's going to be just executed whenever you destroy this coroutine. Does it answer your question or not?
Okay, so this is for me a problem because we call this destroy function, and it's calling co-await on this still valid object, which will then wait. So you will have the imagine that you have the while optional line. You get what you expect.
Okay, I think I see. So when you want to destroy it, and this cleanup is going to happen, will this wait?
The co-await.
Right. No, it's not going to wait. So when you do set done, you are back on your side. So co-await will just freeze like your coroutine and goes back to the caller. So it's not like active waiting.
Okay, so there will be a if in this co-await, which will decide if it's...
It doesn't need to. So the co-await knows how to... So what async close returns knows how to make things right. So if it's a task, and I'm awaiting this task, this is going to be executed, right? We can, everything depends on how you implement this awaiters types, but you can register your coroutine to be run on the other thread. So from one thread, you will be destroying the coroutine, so it will just do the co-await async close, which will be invoked, scheduled on another thread, and then it will just, from your point of view, it will just return you. But then from inside the coroutine, you have got a possibility to close your file.
I think. Yeah.
You can stay after and
Okay.
we can talk.
Thank you, Zbyszek. So there are still doubts, and I could hear the brains working in the background. So thanks a lot for this question.